to talk about, yes, how easy or hard it is to color big real-life graphs. And also, can we have an estimate of how fast can we have an estimate of the number of colors that is required to color a big graph without coloring all the graph? So first, I will recall what is the coloring of the graph. Probably most of you know the definition. It's quite a classical problem in graph theory. So you have a graph which is undirected, and you want to give a color to each vertex, and in such a way that if two vertices are adjacent, they must have different colors. And of course, you want to do this using as few colors as possible. So this minimum number of colors which is required to color the graph is called the chromatic number of the graph. And it is a NP-hard problem, one of the hardest problems in computer science. And yes, let me point out that finding a coloring with K color is equivalent to finding a partition of the vertices into independent sets. Like on this example, you see coloring in 4 colors, and on the right, a partition in 4 subsets. Each subset is without edges. So it's more or less the contrary than finding clusters or communities which represent dense subgraphs. So here you partition into empty subgraphs. So there are many applications of graph coloring. I will not recall all of them. Simply say that, yes, one motivation can be that well, color is important in your life. For instance, personally, I prefer red than white, but it's a matter of taste, of course. So more seriously, I only put some recent papers that use graph coloring in order to do other things, and for which the graph we have to color can be quite large. And also, we have to keep in mind that the problem of finding clicks in graph is strongly related with the problem of coloring a graph. If I have a way to quickly say that, well, I can color this big graph using 7 colors, then I know that I do not have to search for clicks of size larger than 7, because they are not in the graph. So, as I said in this work, I wanted to first test how the sequential algorithm for coloring graphs behaves on very large graph. And also, so is it possible to have a good estimate of the number of colors, only coloring a small part of the graph? And as a byproduct, I can compute a sort of core of the graph for the coloring problem. So there are not many works that consider this problem of coloring big graphs, and only recently. Mainly, they compare many algorithms and to see which is the best for which kind of graph. And also, they try to parallelize the algorithms in order to fasten the coloring process. So I also look at sequential algorithms. So why? Because they are very simple or greedy coloring algorithms. It's the same. So basically, you have a graph, you take an ordering on the vertices, and you color them following this order. And at each time you color vertex, you give to it the smallest color available for this vertex. So this is what is meant by this formula. So of course you can try with very simple ordering, like you use the order, you color the vertices in their order. Vertex 1 first, vertex 2, and so on. But it's not so efficient in practice. Better, you can start with vertices with the largest degree, and second largest degree, and so on. It's better. And even better, you have ordering which are dynamic, so they are not fixed in advance, but they depend on what have already been colored in the graph. So for instance, I will use DSAT-ratio algorithm. I will present it here. So it's due to Daniel Brelas. Basically, for each vertex, we have to store an array of, so for each vertex, we have to know how many colors this vertex has in its neighborhood. And we color the vertices in sequence also, so one by one, and at each time we choose a vertex with the largest saturation degree among those who are not colored, and we color it with the smallest possible color, like other sequential algorithm. And before coming to the next step of the loop, we have to update the saturation degrees, of course. So why I consider this algorithm? Because it's a good compromise between speed, so it is quite fast, and also it is quite optimal. It will color many graphs using a number of colors which is close to the chromatic number of these graphs. So on a small example, so you have here a graph with 9 vertices. You will first choose the vertex F. Why I didn't tell if, so at the beginning all vertices have a DSAT saturation degree of 0, and when you have two vertices with the same maximum saturation degree, the ties are broken by the degree, the simple degree. So here we will choose F because it has a degree of 5. We color it with color red, color 1. And then all the neighbors of F have a saturation degree of 1, while vertices A, B, C have a saturation degree of 0. Then we continue. We'll choose either E or G. We choose E. We color it with blue color. So now vertex G has a saturation degree of 2. He sees two different colors in his neighborhood, and so on. We color it with the third color. And now we'll, DSAT-ratio will choose vertex H, and so on. So we succeed to color the graph using 3 colors and using this order. Well, so we can look at, for this algorithm, which color the vertices in sequence, we can look at the time when the algorithm has to use the one color for the first time, which is, yes, this value. So delta K of G is the time after having colored how many vertices the algorithm will be obliged to use color K. And in particular, we look at after how many vertices colored, he has to use the last color. Okay, here is the last color used by the algorithm on the graph G. And so we look at the ratio of vertices already colored when the algorithm has to use the last color for the first time. So the ratio over the total number of vertices. So for instance, for any graph, delta 1 is 1. For any graph, you will use the first color for coloring the first vertex. Delta 2 is 2 if the graph is not empty, because the second vertex which will be colored will be a neighbor of the first one, so you will be obliged to use a second color. And if we look at the previous example, we have a graph with a DSAT ratio of 1/3. Why? Because we color it with 3 colors, and the color 3 appears for the first time for the third vertex. So 3/9 is 1/3. So the last color, color 3, is used after having for coloring the third vertex. So 1/3 of the total number of vertices. Well, what can we say? It's not so hard to construct graphs with any given DSAT-ratio. So for any values here and any values of number of colors needed, we can define a graph, except for some degenerated cases. So this is a small theoretical part. And now for the experimental part. First, I compare, yes, here on the graph, how many colors the DSAT-ratio algorithm uses as a function of the number of vertices that have been colored. So in red, you have a real graph, which is a collaboration network between astrophysicians. And we see that the number of colors increases a lot at the beginning. So DSAT-ratio has to use more and more colors. And then it is quite constant after for all the rest of the graph. While for the second one, which is a random graph, so I choose a random graph with the same number of vertices, and I choose the edge probability in order that the algorithm has to use the same number of colors, 57, I think. And you see that it is not the same behavior, so the number of colors grows, but quite slowly. And we have to wait until near the end in order the algorithm is obliged to use the last color. So a very different behavior for the two graphs. So, okay, you can say I choose this graph in order to have this drawing, but not. It seems to be the same for other real-world graphs. So I only test on 14 graphs, but I think it will be more or less the same. So you have on the fourth column, you have the DSAT-ratio in percentage. So you see that it is very small on average, a ratio of less than 3%. So it means that for this graph, on average, you have only to run the algorithm only on the first 3% of vertices in order to get a good estimate of the chromatic number of these graphs. Well, not to be too happy, I also run on DMAX graph, which are graphs which have been selected because they are hard to color. So they serve as a benchmark for coloring competitions. And for this, so I group them by category, and for this graph, the DSAT-ratio is not so low. You see, it's quite 19% or less for this one. So for those graphs which are hard to color, we have not the same behavior. So also, when we have this, we can say, well, we only color the first vertices until we reach the last color. We have to use the last color for the first time. And now we can look at what is the subgraph induced by these first colored vertices. So what we call the DSAT core. And we can try to compare it with the K core, which is a parameter, a well-known parameter in relation with the degeneracy of a graph. So I start to look at this, and I look so at two things. So the ratios of the size of the cores over the total number of vertices. So in red you have the size of the K core, so divided by the size of the number of vertices, so it's very small. So we have very small K cores. We have also small DSAT cores in green, but you see that it's not really the same size for each graph. It can be quite different. And in blue, I computed the measure of similarity between those two sets of vertices. And you see also that so I use the Jacquard index, and you see that it is not very high, so quite small. So the K core and the DSAT core are quite different. So we have to look more to see why it is like that. And to conclude, so of course there are weaknesses in this beginning of work. We have perhaps to test on more graphs to see if this DSAT ratio is always small, or if it depends on the category of network. We can test it with other sequential coloring algorithms and DSAT-ratio. I try the natural ordering, and it is not so good than for DSAT-ratio. So we have not small ratios for this ordering. Yeah, well, perhaps it is easy to color real-life graph because in this graph, mainly you have a big click and you have many vertices with small degree. So it's easy to color. So I don't know in what extent this is true. And of course, you can study other types of colorings. There are many variations on the coloring problem with either adding new constraints or relaxing some constraints. And I think this is the end of my talk. Thank you for your attention.
Thank you for your presentation. About the difference between the degeneracy and the DSAT-ratio, do you think that using the core number of vertices to break up times in the algorithm will maybe it explains the differences between those two quantities?
Yes, it's a good idea. Yes, why not?
Because if we take degree in real world networks, you can have high degree for vertex with really low core value.
Yeah.
Because they are only linked to other vertices of the network.
Yeah. I see. Yes, it's a good idea. It's not so hard to test it. Yes, I can do it.
How do you know when to stop your algorithm? So
that's the problem. Of course. Only I can say, well, on average 3%, so I take 10% and it will be okay.
The question is, given a graph, how do you know you've taken enough vertices?
Yes, we don't know if after what will come after. That's the problem. Yes.
I have a question on slide 11. Because this one, you told that the other Shreni graph is chosen such as having the same number of colors in the end. That means, I guess, that the number of edges won't be the same.
Yes, probably. It's a very small probability. I don't really recall, but.
Because I was wondering if the density is rather higher or lower.
Oh well, I think the density is lower for the green. Yes. I'm not sure, but the edge probability is very small. Mm. Ah, well, I have no idea. Yes, of course, we can color vertices with weight. So by weight, you mean if a vertex has weight 2, you have to put 2 colors on this vertex. Yes. Yes. I haven't seen any work on this. But it's a good idea also.
Two questions. The first one is, if I understand correctly, the saturation ratio depends whether we start exploration.
Yeah.
The first node you choose, which method you use to choose
The algorithm says the first node is the node with the largest degree.
the largest degree? Yeah.
But perhaps we can try, yes, at random. So among the vertices with largest degree, we can try at random on few vertices. I don't know, yes, it's...
And it changes a lot or not if we take a vertices at random, let's say.
Mhm.
There is a big difference between the desaturation ratio for vertex with small degree and vertex with large degree. Is it really necessary to carefully choose the vertex? Maybe we can just run
Yeah, perhaps.
more and
I haven't tested this point. Yes, it's a good question. Mhm.
can I ask the second one?
I don't know.
You mentioned that it's easy to construct any graph with a given
Mhm.
desaturation ratio.
Mhm.
And maybe you try to construct a very complicated graph where the desaturation ratio is about 100%.
Mhm.
How does such a very difficult graph to color looks like?
I don't know what you mean by difficult.
I mean,
But mainly you take a big click and you add some leads. Well, you have to say something, but it's easy. But you have many more examples.
if you take, for example, a big click.
Yes, a big click.
That will be close to 1.
Yes, it's 1. Yes. Also for a cycle of with odd length, you color it with 3 colors, and the third color is used only at the end.
Yes, okay.
So, thank you very much for the talk.